Here we're going to look at graphing functions that are non-linear in some way, right? So that just means that they don't form a line. Thus far in algebra that you've studied, um, whether it's in this class, previous classes, in high school, whatever the case may be, you've certainly graphed lines by this point, but you may not have graphed anything that creates something other than a line. So we're just going to explore a couple different types of functions here. And in general, all we're going to do is create a table of values, and that'll help us to sketch a picture of the line we're interested in. All right, so what I'm going to do here is just make a nice vertical line here. And what we'll do is we'll put x values in this column, and then we'll put function values in this column, which is, of course, 2 times the absolute value of x. And what we'll start by doing is just grabbing some x values. I'm going to start with -3. And for this one, I think I'll go and just add 1 each time. And then over in this column, what we'll do is we'll plug in -3 into the function where we see an x, and then see what that results in. So we know that this is an absolute value symbol here, right? So if we take the absolute value of -3, we get 3. So we end up with +6. So this means that I can go and plot the ordered pair -3, 6. We'll do the same thing with -2. The absolute value of -2 is +2. So that gives us 4. So when x is equal to -2, y is equal to 4. When x is equal to -1, y is equal to 2. When x is equal to 0, y equals 0. And then we'll go ahead and plug 1 in. And now what happens is that it looks like the y values start to rebound again. Oops, I forgot my absolute value symbols there, but that's of course because I know that my absolute value symbols on my 2 are just going to keep the number at 2. So absolute value of 2, which is 2 times 2, which is 4. So now we're here. And 6. So there's, I think, enough points for us to get a pretty accurate representation of what this graph looks like. So play and connect the dots there. It turns out that this shape that's being formed is always the shape that we're going to see when we have a function that involves absolute value like this. So it's always going to form a V, right? So all I really want you to do is, if you're asked about graphing an absolute value function, just make a table of values just like I just did, plot the points, and then go ahead and connect the dots. The only little additional thing I need to make sure you do is to always make sure you find the bottom of the V, okay? Make sure you find that. So the reason that's important is, let's say you made a table of values, and in your table of values, maybe you plotted these 4 points here. Well, if you plotted those 4 points here, you haven't found the bottom of the V yet, right? So you need to find that and see how it rebounds in order to get an accurate representation. All right, so why don't you go ahead and try to make a table of values here and get an accurate sketch of this function. Just make sure that you find the point of the V. right? So after you've tried that yourself, I'll go ahead and put my work down here. Okay, so just to kind of illustrate the point I was trying to make, let's suppose that I tried to start in the exact same place as my last one. So here is g of x is the absolute value of x minus 2 plus 3. So absolute value of negative 3 minus 2 plus 3 is the absolute value of negative 5 plus 3, which is 5 plus 3, which is 8. So I have negative 3, 8. So we have this point right here. And negative 4 plus 3 in or negative 4 in absolute values plus 3 is 4 plus 3, which is 7. So at negative 2, I'm at a y value of 7. And so as I'm sketching this, I'm already getting a lot of points, but I'm keeping in mind that I definitely need to find the point of the V before I'm ready to be done plotting points. And at this point, I haven't found it yet, right? I'm looking for it to rebound. It's like this one just continues to go further and further down. Still haven't found it. Now, when I plug 3 in, we get absolute value of 1 plus 3, which is 1 plus 3, which is 4. Okay, now I think I've started to rebound, right? 3, 4. So maybe just do a couple more. Let me get 5. Okay, I think that's enough. Now I've found the corner of the V there. So now I know it's going to look like this. Now, what's worth talking about here for a moment is how to make life a little bit easier on us, maybe not have to plot so many points. And that is understand that it's when whatever's inside of the absolute value is equal to 0 that you're going to be at the corner of your V. So what you could have done from the start is identified that x equals 2 is what makes the inside 0 and the inside of the absolute value. And then you could have kind of used that as your home base and then done a few on this side and a few on the other side. And then that would have made it so that you'd quickly find the corner of that V and it wouldn't take you quite so long and not have to plot quite so many points. So those are absolute value graphs. They form a V. Make sure you find the corner of the V when you're making your table. All right, the other type of function is what we would call a quadratic function, or one that makes what's called a parabola. So this is when we have x squareds involved. We're going to study these in more depth later, but here we're going to study them just from that standpoint of being able to create a table of values and see what it looks like. So here's a table. So x is here. F of x is equal to x squared minus 4. So we'll plug in some values. If I plug in negative 3 for my x, let's remember that when you square a negative, it turns to a positive. So you actually get positive 9 minus 4, which would give me 5. So at x equals negative 3, we're at 1, 2, 3, 4, 5. At negative 2, squaring negative 2 turns it into a positive 4. So 4 minus 4 is 0. That puts me here. Do the same with negative 1. So at negative 1, we're at y equals negative 3. At x equals 0, we'll be at y equals negative 4. And of course, squaring a positive 1 keeps it positive. So now at x equals 1, we're back to negative 3 again. And at 2, we're back to 0 again. So it looks like we have the same kind of rebounding effect that we had with absolute value equations or absolute value functions. So then we're at 3, 5. All right, so here we don't want to connect things up with lines, okay? Because clearly these do not all lie on the same line. So we're going to have to curve this a little bit more as we sketch the graph. So there's what it looks like. So this is called a parabola. And, I don't really like saying it quite like this because it's not a U, but if we were using the letter V to describe the last one, the letter this would be closest to would be a U. And so just like when we were doing absolute values, we wanted to make sure we found the corner of the V. We also want to make sure we find the bottom of the U, or sometimes these things can be turned over and flipped. In that case, it would be the top of the U, but we want to see the rebounding, right? Just like we did with absolute value functions. All right, so go ahead and try that with this one. Make sure that you're able to see the rebounding effect, but go ahead and pick some x values, find their y values, and then see if you get that same parabola look. And then unpause and we can compare notes. So here's the table. Now, sometimes here's what's going to happen to you. Let's say I'm just going to pick a number at random. I'm going to say, what if I decided to start at negative 5 just to see what I got? And of course, my y is equal to g of x, which is equal to 2x squared minus 8. So if I did 2 times negative 5 squared minus 8, I'd get 2 times 25, right? Positive 25 minus 8, which would be 50 minus 8, which would be 42. Okay, so if I went out to x equals negative 5, that would mean I'd have to go up to y equals 42. Well, that might be correct, but it's not very useful for sketching the graph. So if you notice that, if you get a y value that's just way off the grid, then pause for a second and think, okay, what kind of y values are going to give me reasonable numbers? Or excuse me, what kind of x values are going to give me reasonable numbers for my y values? Well, negative 5 just was too big after I squared it, right? So you want to be thinking about numbers that don't get that much bigger after they've been squared. Okay, so let's go ahead and pick some things like negative 3 might be a little bit better. So I'm thinking negative 4 is squared is 16. So I'm going to skip over that one. Let's see if negative 3 gives me something more manageable. That'd be 2 times 9 minus 8. 18 minus 8. Ooh, 10. Okay, so negative 3 with 10, well, that's manageable because here's 10 right up here. So I can actually see that dot. All right, so now I think we've got some x values that are going to make some sense for us. So 2 times 4 minus 8, that's 8 minus 8, which is 0. So looks like at negative 2, we're at 0. So 2 times 1 minus 8 -6. Okay, so looks like we're right down there. And when we plug 0 in, you of course get -8. And then when I plug 1 in, there's where I see the rebounding. Right? 2 minus 8 is -6. 0. And you can probably guess what this one will be, right? Because of course, when we square the positive versions of those negative numbers that we started with, we're of course going to get the same answer. So there's our parabola. I've certainly graphed better ones before, but you get the idea.